I'm Manjunath Gorentla. I'm an architect at NVIDIA networking. Today, what I'm talking is about our project UCC. UCC project is part of UCF consortium. And it's really, I'm presenting this on behalf of our working group. We have worked really hard over the last 6-7 months to develop this project. So I'm talking relatively softly. If you can hear, if you can't hear, please let me know. It's very early in the morning and I don't want to wake up my kids. So again, as I mentioned, this is really on behalf of our working group. The project is unified collective communication. And the goal of the project is really to develop an API library that supports multiple programming models. And we have a unified collective stack for multiple runtimes. If you have part of UCX face-to-face last year, we tried to motivate why we need such a stack. And over the last 6-7 months, we have worked towards this goal. So this statement is more goal of the project rather than the state of the project today. So we are working towards that goal. What I wanted to do in this talk is, I wanted to go over our experience in the working group while designing this stack. What I'll do is in the rest of the talk, I'll talk about design challenges and what the property of our solution should look like. Provide a overview of very brief overview of our API, particularly of our candidate solution, and then the reference implementation status and what's our plan for next few months and next year. So when you want to design a collective stack or any stack, sorry, a collective stack or any stack that wants to support multiple programming models, multiple workloads, and multiple environment is, you end up with a variety of semantics. You need to support many semantics. I think over the last few days, you've seen that challenges, solutions, and what was done with UCX. And collective adds another dimension to this because of the scale that we have to worry about as well, right? So another challenge is when we are unifying a stack for HPC and say DL ML workloads, right? The workloads have different sensitivities. You have to deal with this. And because of the heterogeneity of these workloads, you have to worry about how you schedule your resources. So you need to have your solution should have very flexible resource scheduling model. And also some workloads care about ordering. Some workloads don't care about ordering. So we need to have a flexible ordering model. And we wanted to unify software for both hardware and software transport that's used for collectives. The consequence of that is a complex resource management. Say that you have supporting both hardware collectives and software-based collectives. You want to first use hardware collectives. And when the resources exhaust, then you want to move to software collectives, which means that your resource management becomes much more complex. And there is typically a gap between software-based collectives and what hardware-based collectives provide. So you need to kind of efficiently bridge this gap. And another challenge is unifying parallelism and concurrency, right? What I call concurrency is here you have one collective and you want to progress this collective and also you want to progress the computation, right? And then parallelism you want to have many independent collectives progressing at the same time. This doesn't necessarily complicate interface, but what it complicates is the implementation. And then other challenge that I think it's important to call out is unifying execution models for CPU, GPU, and DPU. So I call this two-way execution model and one-way execution model. I could call in a different way, but let me make it clear what I meant by two-way execution model. If you take collectives, right, today you can invoke on a CPU thread and execute on a CPU, progress on a CPU, and then complete on a CPU. And what I call that is a two-way execution model. The reason is because you can have a closer interaction between thread invoking and a thread executing the collective. The overhead to interact is much, much lower. But if you go to something like, say, GPU or TPU, you typically invoke collective on a CPU thread and probably complete on progress and complete on a different thread, either a GPU or TPU. When you have such kind of execution model, you want to keep your interaction very, very low because the overhead of interaction is much, much higher. Typically, you just want to post the collective and just collect the value, right? So the challenge is we have to unify this execution model. I don't think we necessarily solve this problem yet. This is something that we are working or will work in next coming months. So as we unify the stack, right, there's many stakeholders, there's many workloads, and there's many solutions as well. So I think it's very difficult to come up with one ideal solution. But I think as a working group and people, all the folks participating, right, they have experience about implementing middleware for a very, very long time. I think we can recognize what the properties which we want in a solution, and we try to make sure that we kind of hit those targets. I think this is no-brainer. The first bullet that scalability and performance is important, right? So you want to have an efficient implementation. If you don't have a efficient and high-performance implementation, adaptability becomes a problem. And we know that when we are supporting so many workloads and so many runtimes, we will never cover all possible functionalities, all options, and so forth. So we have to keep our API kind of extendable and our implementation modular. And also, again, as we support many use cases, what happens is there is a set of users who doesn't care about many parts of the implementation or many parts of the API itself and the functionality itself. So you need to have a solution where you have a kind of opt-in and out model. A certain path requires a certain workload requires certain functionality. You want to basically have a way to opt in, and if you don't want it, you want to have a way to opt out. So I think another another important property, in my opinion, for the such stack is to have an explicit API and semantics over implicit. Whenever you have a choice, you should want to choose explicit features and explicitly lay out the functions. And it's easier to move from explicit to implicit model than the other way around. And you will see that throughout our API and design that we make this. This is very evident in many parts, particularly if you look at our, say, ordering model, synchronization model, and even the resource allocation model, and also threading model. Threading model is something that many stacks would have already adopted. Right. So I think this becomes the next property is minimizing the API surface area, right? I mean, this is again something we all know that we want to reduce it. And I think I believe that we have really worked hard on doing this. There's many advantages for this, right? One is a new user coming in doesn't have to understand a lot of interfaces. And also, again, because we have many stakeholders, we want to design such that if somebody wants to just understand a bit of API and semantics and go into detail only when it's required, right? We want to design that way. Of course, there's other properties that's important. But I think when we are unifying, building a stack that's for multiple stakeholders, right? I think these properties are very important. Our solution, I think we kind of have a right solution. You will see why I tell that. If in UCC, if you want to understand, right, there's only a few concepts that you have to understand. What I call abstractions is really we try to think from a resource perspective, start from our resources, and then abstract those resources, and then we have some operations on the resources. I will talk about this. I'll spend a slide on each of these resources so that you understand what I mean. And then properties, right? We express properties on these abstractions. For example, this is a way for us to have an opt-in and opt-out model. For example, what are the properties? Properties could be a collective type, ordering, what ordering model you want, what synchronization model you want, what threading model you want, and in future, what memory type you want. This would be all properties. These properties could be cross-cutting. For example, you can express the collective types on a library, on a context, on a team. And currently, the way we model these properties is more of a preference. What I mean by that is you have a resource abstraction, and on that you express the properties. And this is a way for the user to tell the library, these are the properties they would like on the particular resource. And to figure out what actually library provides, we need to query it. So we also have thought about extend its properties to more like rather than preference, having them required. So far, we've found that expressing that as required is more of a convenience rather than it requires. But as we work through multiple more use cases, right, maybe later year, we might find this requirement that we want to express this property as a required feature. So we will see. So overall, right, these are the three concepts that you really have to understand in UCC. So challenge is really mapping all the semantics, functionality features to this concept. I think overall this approach has worked. We kind of have an API that I think is relatively stable so far, and we have experimental implementations, and we see experiment from the experimental prototype implementations that this API seems to work and provide efficient implementation. I'll share more. So let me spend just a slide on it. And I think if you have heard me before, this is probably more familiar to you. So what we have is a collective library is one abstraction that we have, communication context, teams and endpoints, and then we have operations. What's a library? So UCC library handle encapsulates all the resources related to group communication. So you want to start all the operations after initializing the library before finalizing the library. Well, some of the properties on this library is collective types, which basically says that what collectives is supported by the library. So it's again, the model is like user asks what collectives they would like, prefer, and the library reports saying that this is what we implement. Same with the thread model. User will ask what thread model they would like, and library says that what thread model they have, right? What's implemented. And the synchronization model, similarly, we could have synchronous collectives or asynchronous collectives. Some of the operations of the library is pretty standard, initializing and finalizing the library and querying the properties. So this is a screen grab from the header file. And if you see, right, we have a pretty detailed description for each of it. You are initializing the library, and we pass properties as params. So we decided to, I think we played with multiple names. Then we decided that we will try to keep this naming convention similar to what UCX has, so that it builds familiarity across the UCF projects. So you pass in what properties you require, and then you can you get the handle back, and you can query what the properties attributes you have. So next is next abstraction is a context handle. It basically is really abstracting your local resources, and this is a way for the user to express the network parallelism. One way to use this is to encapsulate local resources. It could be IBQ pairs, sharp trees, or UCX worker if you have software-based collectives, for example, in our case. And this is where we try to do kind of a resource sharing between either multiple collectives or multiple teams, and so forth. Some of the properties on the context would be like, when you create this context, you want to say that whether this is a shared resource or an exclusive resource, and thread model and synchronization model. You can see now there is a pattern about each of these, right? There is abstraction, there's properties, there's operation. And also you can see that some of these properties are actually cross-cutting. So I think the way this is expressed minimizes the API, and how much somebody has to learn about the API and the semantics. This is again a graph from the header file. It's an API for creating the context. So previously we created a library handle, we pass in the library handle, and then parameters again. Basically properties are passed as parameters here, and then you create a context object. So you have a library, you built a local resource. Now you want to build a group resource because you want to do a collective operation. And this is called team in UCC. It actually encapsulates the global request for collective operation. I think if you want to map a API programming model, right, you want to map the communicator to the team here. And this is a place where local resources negotiate and with the other local resources and build a group and converge on the semantics. I think properties is a typo here. Let me see. I think I have. Let me go to the properties in bit detail because it's more interesting here. So this is the interface to create a team. It's a non-blocking operation. However, you have you can post only a single operation of this. And so first we build the library, then we build the context, and then we pass in multiple contexts or a single context, and then build a group. Who participates in the group? I will explain that how we build that. So you can pass in a single context or multiple contexts. The reason is, remember that context is is really represent your local network resource, right? So if you want to give more network resources to a collective, you want to give more context. And of course, you can share this with multiple teams. So some of the properties of teams are ordering. You can tell. I don't know if you guys can you guys see my pointer, mouse pointer?
Yes.
Okay, thanks. So ordering, you want to tell whether the collectives are ordered on this team or not. And then we have outstanding collectives, which means that number of outstanding collectives that you can post. Remember that this is what the user asks the library, and this is what user library gives to the library. And then there is a list of things: endpoint, endpoint list, endpoint range. What this together is doing is like in a group, right? You need to have identifier for each of the participant of the group. Typically, when you are integrating such library into other programming models, parallel programming models, right, you already have this information. For example, in MPI, you can think about this as ranks, right? In SHMEM, you can think about this as PE number, and so forth. For that, you can actually, you already established the identifier. So identifier will have some properties. For example, it has to be unique. In some cases, it has to be contiguous. In some cases, you don't have to be contiguous. So if you already have this information, you provide this information. If you don't have this information, this interface will let you build that if you want to. And this is a synchronization model that I explained before. You can have asynchronous collectives or asynchronous collectives. And so one way to build a group is you pass out of band collective operation. Say, for example, in MPI, probably you can build this. You already have this information when you start. Typically, you start with some runtime which can give you that. If you don't have it, we could implement that. But then as a library, you make certain assumptions if you end up doing that. So we have a library, we have a local resource, we have a group resource. Now we are ready to launch a collective, right? Like these are the interfaces to launch a collective. I think this UCC collective unit is a group operation where you initialize the buffers for building the collective, and you don't really post it, and then you post it with the post operation. And I think this model works if you have both the one-way execution or two-way execution model. We have experimented with it, but not implemented a say offload model using these interfaces yet. So we are about to do that. So, and this is more of a convenience function to merge these two. And then once you can finalize the collective. Once you finalize the collective, you have to call the init again. If you don't finalize it, you can post it again. Of course, you can verify where is this behavior using passing the right parameters. I think I talked about this slide already. So I'll skip this slide. Okay, so where we are today. So we have APIs, specification kind of is really documented well. And of course, it's not complete. We will, I think it's pretty close to complete. I would say that if you find any bugs, we'll fix it. So at this point, we discussed this semantics API for probably many months, and we had a PR out in August, I think, and we still reviewed it, and we merged it in October. At this point, we feel pretty comfortable as a working group, and we are starting to develop the code. At this point, our specification is a bit ahead of the code itself, and we don't expect to change. But of course, if we find a bug or something, that we will fix it. And you can download from GitHub today. So as I mentioned, this is an effort of many people who have participated regularly in the working group and who have provided input in other meetings as well, right? I would like to call out two implementations here, particularly XCCG that Huawei and Alex and his team is working on, Excel that the NVIDIA team is working, right? Besides this, we have learned a lot from our HCall experience and IBM from PAMI experience and MPH team and also OpenMPI team, right? They've all contributed ideas, manifold. So, and this is, we hope this is really convergence of many good ideas that we had over the last 10 years. So, well, what's Excel? So Excel is a experimental, I don't think we should call this experimental, but it's a prototype implementation of a UCC API. So it started differently in the sense that it was not necessarily exactly UCC API, but as we started discussing the API in the working group, and we started to converge more towards the semantics and API that working group was working towards. So it uses a namespace, Excel instead of UCC, implements a subset of UCC API. Code base, as I mentioned, is evolving with the discussions that we are having in the working group. We feed into, we learn, we feed into the discussions. Whenever we have a way to make a decision, we experiment here and do it. And it's based on hierarchical. It's based on hierarchical design. And if you are familiar with HCall or Cheetah, you probably know what I mean by this. And I don't want to spend too much time on this. Later, there are more talks talking about this. So at this point, it supports both software and hardware transports. It has an implementation based on UCA. It has an implementation about Sharp. We started to experiment with GPUs, and we have integration with OpenMPI and PyTorch, and it is reused. I just want to just like a peek into the results, even though we call it experimental, but it's not really, the performance is as good as you can get. So on the x-axis, you have number of MPI ranks. On y-axis, you have latency in microseconds. It's MPI already used benchmark with 1 MB message size. And we can see that the performance is good and scalability is good. So similarly, this is more of a demonstration about how we can use hardware broadcast. On the x-axis, you have number of ranks, and y-axis, you have latency in microseconds. And you can see that whenever you are using hardware collectives efficiently, you not only get performance, but also scalability, right? The scalability is really good. And as I mentioned, another implementation that's feeding our design decisions is UCG. This is from Huawei. Alex provided some results, and I mentioned that they're working towards more results, and we'll have a detailed talk about XUCG later this morning from Alex and his team. So from what I understand, on x-axis, we have ranks. This is on a shared memory. And on y-axis, again, you have latency in microseconds. And the benchmark was OSU, I think, OSU MPI broadcast, and a small byte on Rocky. The comparisons here is between one implementation where which is called P2P, where you are using point-to-point communications to implement the broadcast, and the other is using multicast. I think following this talk, there's more talk about the multicast. And similarly, as all reduce, and as you can see on x-axis, it's following the same theme. On x-axis, you have MPI ranks. On y-axis, you have latency in microseconds. Again, the difference is between these two implementation. One is using point-to-point, and another is using multicast. So I will call out all the talks that we have following this talk. So first three talks is about UCG, and the other talk is about Josh from NVIDIA will present about how we are using UCC API and implementation for scaling deep learning workloads. So typically, we always talk about HPC workloads. I think this will be a good change. So where we are from a UCC, as I mentioned, right, UCC is converging all this implementation, all these ideas, and where we are from an implementation perspective. Okay, let me talk about that, how we are going to converge from an implementation perspective. This is really of a goal rather than, again, a reflection of a current state of the stack. So we expect our applications or programming models to use our API. And as I mentioned, right, we feel pretty comfortable with what we have designed, because we have experimental prototype implementation that actually already does integrates with PyTorch and OpenAPI. And the core component here, what will it do is basically choose the right implementation here. In collectives, is pretty complicated. I think if you attended Yossi's talk on Monday, he explained how they are going to choose each lane Tuesday, how he's going to choose the protocols and so forth. With collectives, this becomes much more complicated. You have to deal with many algorithms, many implementations, scalability, and so forth. So I think we can get some ideas from how UCX does, and probably we can incorporate those ideas as well. And this is also a very critical component, right? We want we have to get it right. So we anticipate that we expect that we are going to support multiple implementations because the collective is such a huge space that you can come up with many implementations. So at least potentially we expect that 2 ways to implement it. Even though there is 2 ways to implement it, there is a lot of infrastructure that's pretty common. And if you decompose these implementations, right, you can have many of the primitives that is implemented and shared. And the way we expect to build that is we want to build a schedule of a collective, and then decompose those primitives and execute those primitives. So it's pretty high level at this point. Hopefully next year we will provide more deep dive into each of these boxes. So, and we expect that maybe some of these collectives doesn't necessarily require high quality implementations. For those edge cases, we rely on basic implementation. Our idea is to support everything. But now some of the edge cases, some of the edge use cases, we might just go with basic. And say that some vendor wants to use all our infrastructure. Maybe they want to just optimize, say, for example, all reduce or something, right? And they want to keep it proprietary. We want to provide a way to integrate such functionality as well. And we plan to support at least one software-based transport, very likely UCX. And then we might have a proprietary or more specialized shared memory implementation transport. And then we expect to have hardware-based collectives on Sharp, multicast, and maybe more. So to show the status of the code itself, I grabbed a screenshot from yesterday, I guess. And you can see that we are making a lot of progress. We have about, seems like 85 commits. And I think code is evolving a lot. We have basic library initialization and so forth. And I think there's a pull request from Valentine from NVIDIA to build some of the common infrastructure. So, and Alex brought the Google test. Thanks, Alex. So we are evolving. It takes time, but I think we are making very good progress. So what we plan to do next year is, with the current resources that we have, we expect to release a reference implementation in Q1. What we'll have in the early release is API and semantics and basic implementation of barrier broadcast, all reduce and all job. We expect to support multiple threads, and we expect to integrate, have a driver for OpenMPI, have a driver for PyTorch, and unit test infrastructure. I think we already have merged some, but we'll have more, and we might have multiple implementation of this important collective operations. So what we want to do is, once we do early release, we want to give it to early adopters and get feedback, and then make another release likely Q2 2021. And then we plan to have series of releases, mostly focused on performance and stability, and not try to change too much of the API. And then we will expand into version 2, where we'll have a series more advanced features, meaning that better way to do algorithm selection. This is a really complicated topic, so we want to give out time. So in a version 1.0 series, we will have more basic way of selecting, but we will expand that. And we plan to have a complete GPU support in a 2.0 release. What I mean by that is, we want to do collectives when the data is in GPU buffer, and also we want to support, say, executing the collective on the GPU. And we would like to have support for GPUs and PGAS collectives. And of course, we require a good way to abstract the topology and express that and so forth. And we kind of pushing that to 2.0 release. And it's not to say that we don't want to do this. It's more of saying that given the resources, we want to get something before adding advanced capabilities. So there is plenty of work, and we would like first there's many participants in the working group, and we meet every week and we discuss, and we've been doing this for close to a year now, more actively for 7-8 months, and we have a lot of work to do. As you can see, we have more to do than what we have done, and all kinds of contributions are welcome. Design, documentation, code, anything that you can think you can contribute, please join the working group. And there's multiple ways to participate. As I mentioned, we meet every week on Wednesday. We have a GitHub repo where all our work is open. You can contribute there. We have a Slack channel. If you want to participate, please just ask me, I'll give you an invite. And of course, we share a mailing list with UCX community as well. So with that, I would like to thank all the working group members, and also I would like to thank you guys. So at this point, I want to open up for any kind of discussion or questions and so. Thanks.
Hey, Manju.
Yeah, Josh. Yeah.
Hey,
go ahead.
so what is there like a date or a date or a time or a place where you will, officially ratify the API?
So I would say that we merged the API. This is kind of a ratification, and this is of a convergence of all the discussions that we had in the working group.
Mm-hmm.
And we don't. I would say that is a ratification, in my opinion. What we want to open up a little bit is like if we find some bugs in the API, right? We want to fix that. Imagine there's many standards that we have worked for 20 years and we still fix bugs. So I don't think we are anyway perfect, right? So we want to keep open up on that. So.
Yeah. Oh, okay. So, gotcha. Okay, that helps.